Hey, all right, here we go. Uh, this is a little engineering design calculation using our knowledge about pneumatic pistons. Okay, so you reviewed how pneumatic pistons work, and we have in stock a pneumatic piston right here. And our goal today is to do some calculations to figure out if this piston, actually a pair of pistons, one on each side, will be strong enough to lift this arm, like so. Ooh, up. Now, this pivot point and this pivot point are pretty dialed in so that the arm retracts behind this line like it needs to, and then also automatically stops because it's at the end of its extension right where we want it with the ball. So that's the general setup. We need to figure out how much intake cylinder force each one of the cylinders can provide. And remembering that force equals pressure times area, we need to figure out the area of the inside, that effective area of the inside of that piston. If you remember that inside of the piston, there's going to be area for the piston to act on the rod to extend it. And so we can take a look at some calculations here where the cylinder that we have has a bore diameter of 7/16 of an inch and a rod diameter of 0.19 inches. We're going to be taking a look at that piston area as pi r squared, so that's the diameter over 2 squared, of about 0.15 inches squared for the area of the piston. And then we'd have to subtract the rod area because the air does not get applied to that surface. And so we have an effective area of about 0.13 inches squared. If we take our pressure from the air cylinders, the air tanks, of 60 psi and multiply it by 0.13 inches squared, we'll get about 7.8 pounds of force. Okay, so that's the force that each one of these cylinders is able to apply to the arm. You'll have to imagine the other cylinder on the other side. Now, it's not acting in a straight line. It's not acting perpendicular. So we're going to have to take into account that it's at this angle, okay? And we have talked about torque before, but let's just review a little bit. Torque is a twisting force, and so we've got a wrench here with a nut, and torque is greatest when the force is perpendicular to that radius, pulling down. If you're pulling at an angle, the torque actually decreases because it's only that perpendicular component of force that acts to twist the nut. And then if you pull directly in line, parallel with the moment arm, they call it, then there's no torque, right? That's not, if you pull on a wrench, it's not going to twist the bolt. You pull sideways and it twists the bolt. So there's a little bit of trigonometry that we actually have to do in order to figure out how much of that force acts to create the torque. And we use what's called a sine function, and that's dependent on the angle. Okay, so it's a little bit of math here, but it's nothing we can't handle. Let's take a look at our forces. Okay, so we've got this piston pulling up, but it's not pulling up straight, it's pulling up at an angle. Now, there's two pistons, so we're going to multiply the force by 2 to give us 15.6 pounds. The arm attachment point is a distance of 2.9 inches away, and then this angle is 26.9 degrees. So that's the torque that's pulling up. Now, if it was pulling up on something very light, it would be fine. But this arm actually has weight, and we can estimate that weight as about 2.5 pounds. And we did this using our CAD model. And the center of mass, or the effective position of this, also calculated. Actually, I can show you that real quick, how that gets calculated. If we look at this arm and we select all of the components of it, that too. You can come down here, the bearings too, because the bearings are heavy. And I'm going to hide myself, see you later. If we do the calculations, it can convert and calculate a center of mass. So if we come over about 7.8 inches, that's how far away, cantilevered out, this arm is from the point of rotation, which is the bearing here. So our effective distance away for the center of mass of our arm is about 7.8 inches. Now, at the worst case scenario, it's going to be 90 degrees to gravity and the arm, so we're just going to use the max of 90. All right, so will this 15.6 pounds of force be enough to overcome the 2.5 pounds of force, factoring in the moment arms and the angles which they act at? That's the big question. We haven't had time to actually test this, and we want to be prepared with alternative options in case it's not. So let's take a look. The torque acting on the arm by the piston must be greater than the torque applied by the weight of the arm. Here we go. We've got that 15.6 pounds of force at 2.9 inches. Looking at the sine of 26.9, that turns it into about 20.5 inch-pounds of torque lifting. And then our torque arm weight, 2.8 times 7.8, that's pounds, inches, is 21.84 inch-pounds. So that is really close. That is really close. There's not much margin for error there. We may need to come up with a backup plan. Now, that's it for this ed puzzle in terms of intake arm engineering calculations. We looked at pressure in a cylinder and applied torque to a system to see if we need to have a backup plan for maybe either getting a larger cylinder, or perhaps using a spring assist. We got options, don't worry. But that's the kind of engineering calculations you would do as an engineer if you don't have access to your mechanism. All right, guys. Signing out.